Here are the circle theorems questions from Past Paper Penguin. Now in this question we are asked to find angle APB, which is this angle here. Okay. Now if you look carefully, let's see if we can work out which circle theorem we're going to use. Well, I have the angle at the circumference, and from those same 2 points A and B I have an angle at the centre. So what I'm going to do is try and work out this angle here. To do that I'm going to use this triangle. It's an isosceles triangle because both of these are radii, yeah, both radius of the circle. That makes this thing here 38 degrees. Then I'm going to add those together, that's 76. And I'm going to subtract that from 180, which gives me 104. So that angle at the centre there, this one here, is 104 degrees. So let's write that a little bit more clearly. And now we're going to use our circle theorem that the angle at the centre is twice the angle at the circumference. So 104 divided by 2, so this one here is 52 degrees. This question wants us to find angle EFC, which is this one here. Okay, the angle we're given is this 50 degrees here, so we're going to use this somehow. And what we have got is we've got this triangle here, and one of the points of that triangle meets this tangent here. So that means that we can use the alternate segment theorem to find this angle here. That angle there that I just highlighted in red, that's going to be the same as that 50 degrees using the alternate segment theorem. So this one over here is 50 degrees. Then these two sides, although they don't look it, we're told that they are equal. So it's an isosceles triangle. So this one is also 50 degrees. And now to find that remaining angle, we're going to add those two things up. So 50 plus 50 is 100. And then we're going to do 180 subtract 100, which gives us 80 degrees. So that one there is 80. Next we're asked to find angle CDE. CDE is here, so this angle here. It's important to notice that here we're told it is a cyclic quadrilateral. So in a cyclic quadrilateral we know that opposite angles sum to 180 degrees. Because we found that this one is 80, CDE must be 100 degrees for them to add up to 180. So CDE is 100. This question again gives us a cyclic quadrilateral ABCD, and we're given two of these angles, and we are asked to find angle BDA. BDA, that's this angle here. It's only one mark, so it can't take that much work. So I'm just going to draw over. So there's our angle BDA. Yes, and here you can find that there is another angle that comes from those same 2 points on the circumference. Sometimes I get my students to look for this kind of bow tie shape with all corners on the circumference. And when you've got that bow tie shape like that, that means that this angle here is equal to this angle here. So those two are equal. The ones at the bottom would be equal to each other too, but not 34. They might be something different. So this one up here is 34 degrees. Okay, that's using angles in the same segment. For BCD, let's quickly get rid of these lines that we don't want anymore. So for angle BCD, BCD is this one here, from B to C to D. Here we're going to use the property of a cyclic quadrilateral. So opposite angles in a cyclic quadrilateral add up to 180. So that means BCD is going to be 180 take away 74, which is 106 degrees. And then in ABD, that's this angle here. I think here we're just going to use angles in a triangle, add up to 180 degrees. So I'm going to do 74, add 34, and subtract from 180. 74 add 34 is 108. Subtract that from 180, and we get 72 degrees. In part B of the question, we're told ADX is similar to BCX. I'm going to make a quick sketch of those two triangles. So that'll be my ADX, and my BCX is going to look something like this. So ADX, BCX, and let's fill in the information that we're given. So we know that this one here is 34. We know that this is 74. We're told that BC, let me fill in this as well, 34 here. And then we're told that BC is 4.5. AD is 9 centimeters, and CX is 3.3. We also know, and this is important, we know that this angle and this angle are equal using vertically opposite angles. So that means here that this angle is equal to this angle, and we could actually work it out if we wanted to, but there's no need. The reason that's useful is to tell me which sides correspond to which. So you can see here that this side AD is opposite that angle. That one must correspond to this side CB, which is opposite that angle, okay? And that's telling us what the scale factor is from that larger triangle to the smaller triangle. If I do 9 divided by 4.5, then I get 2. That's telling me this triangle has been enlarged by 2, okay? So now I'm trying to find the length XD, this one here. Well, that side corresponds to this side here. So I'm going to do 2 times 3.3, which gives me 6.6 centimeters. This question gives us these 4 points on a circle, and straight away you should notice that we have a cyclic quadrilateral because all of the 4 points are on the circle. And we're told that this is a straight line, and we're asked to find angle ABC. Okay, ABC, so that's the angle we're trying to find. Because it's a cyclic quadrilateral, what we'll do is we'll work out this one first, using angles on a straight line. That is 104 degrees, they have to add up to 180. And then opposite angles in a cyclic quadrilateral add up to 180, so that means that this one here must be 76 degrees. In part B, this one looks a little bit more complicated. First, we're asked to find angle STR, that's this angle here. Okay, I'm going to look if I have any other angles subtended by SR. So, there's my STR. Let's see if there's any other angles on the circumference which come from those same 2 points. There's this one up here, okay? Because this one is also on the circumference. And again, we've got that kind of bow tie shape. And that means that this angle and this angle are equal. And we know that this one here is 25. So that means this one down here is also 25 degrees. Okay? So, using angles in the same segment, this one is 25 degrees. Next, we're asked for QOR. So QOR is this one here. This angle is at the center. When we have an angle at the center, often the thing we're going to be looking for is an angle from those same 2 points, which is at the circumference. So let's just have a look and see if we can find anything like that. So here's our angle QOR. So from those same 2 points, I'm looking for one that's at the circumference. There we go, this one here. So we have this angle here, which is at the circumference, which comes from the same points Q and R. and we know that the angle subtended is twice the angle at the circumference. So if that one is 40, this one at the centre is going to be 80. So actually that diagram looks quite complicated, but the question wasn't too bad. In this question, again, we've got a cyclic quadrilateral, and it wants us to complete these statements using T, U, V, W. So angle something is equal to angle something. Okay, so the ones I know where we've got equal angles is the one with that bow tie again, the angles in the same segment. And I can see that these two angles here are both subtended, both come from these 2 points here, A and B. Okay, so that means that these two, through angles in the same segment, those two angles are going to be equal. So I'm going to write angle T is equal to angle W. Then we're told that angle DAB equals 75. So let's just write that in. DAB is 75 degrees. And we're asked to find DCB. DCB is all of this one here. And we're going to use the fact that this is a cyclic quadrilateral, so those two things have to add up to 180, which makes this one here 105 degrees. In this second part, when they start to give you lengths like this, it's often a question about similar triangles. We'll fill in the lengths first, so AB is equal to 8, AX is 6, BX is 4, and DC is 5. And then again, I'm going to make little sketches of the triangles separately here. So the triangles that I've just drawn are this one down here, the one which it's given me all the lengths for. So ABX with 8, 6 and 4. And this one here is DXC. The reason I've chosen those triangles is, well, first of all, it's given me all of the lengths of this one. Here it's given me one of the lengths of this one, and the thing I'm trying to find is CX there, one of those other lengths. So it's really the only two triangles I could have made. For them to be similar triangles though, I need for some of these angles to be equal. And again, it's using angles in the same segment. So this one here, BAC, is going to be equal to this one here. So those two angles are equal, the angle at D and the angle at A. So let's colour those two in blue, so those two are equal. By the same reason, this one here is going to be equal to this one here, okay? Gives me that same bow tie shape, so the one at B and the one at C are going to be equal. And finally, using vertically opposite angles, these two are going to be equal. And that's why we have two similar triangles. And now, with those angles, you can see that this side here, the one between the green and the red angles, is the one we want, so it corresponds to that 4. First though, we need to find the scale factor. So let's do the larger one divided by the smaller one, so 8 divided by 5 is our scale factor. Okay, you can leave it as a fraction or you can change it to a decimal, whatever you prefer. 8 divided by 5 is 1.6. Now I'm going from the bigger triangle to the smaller one, so I don't want to multiply by 1.6, I want to divide by 1.6. So I'm going to do 4 divided by 1.6, or 4 divided by 8 over 5. If you were going to do that, you'd need to remember to keep flip change for dividing the fractions. And I get 2.5 centimetres. In this question, we've got a tangent to a circle, and we've got a triangle connected to it, which means it's an alternate segment theorem question. Let's just highlight that triangle, okay, and the tangent there. And what I tell my students to look for is kind of like a Z shape involving this triangle, but but it's not alternate angles, careful. So it's not this one here that's the same, but it's this one kind of at the end of the Z shape that's the same. So that means that this one up here is going to be 39 degrees. Okay, that one and that one are the same. And then I'm just going to use angles in a triangle. So I'm going to add those two angles up there, 62 and 39. That makes 101. And then I'm going to subtract that from 180. Okay, to find that last angle in the triangle. 180 take away 101 is 79 degrees. Again, we've got triangles and tangents and no radius. So again, this is kind of indicating to me that it's an alternate segment theorem question. Now I'm trying to find angle X. So what I'm interested in is that triangle which includes that angle X. Okay, and be careful because there are two triangles here and two different angles. So it's really easy to, they're trying to make this question difficult. They're trying to confuse you a little bit here. So then I'm looking for the angle between the tangent and that triangle there. And that's that whole thing. Okay, again, with my students, I'd be talking about this kind of Z shape, but it's not alternate angles. It's the one at the end of that Z shape and that one there. Okay, so I need to add these two up. So when I add those two up, I get 72 degrees. So that means that this one up here is also 72 degrees. Okay, now I found that angle there. Let's get rid of some of those lines which are a bit in the way and a little bit confusing. Okay, so this one here is 72 degrees. Now it's important to spot that this is an isosceles triangle because those two sides are equal. So this one is also 72 degrees. And then to find X, I'm just going to use angles in a triangle. So I'm going to add those two up. 72 add 72 is 144. And I'm going to subtract that from 180. 180 take away 144 is 36 degrees. So X is 36. Already in this question, you should be able to see that we have a tangent there and we don't have a diameter or the radius. So this question at some point is probably going to involve the alternate segment theorem. The first part of the question asks us to find angle ABD. ABD is this one here. Okay. Now we don't have any angles down here, so we can't use the alternate segment theorem yet. So I'm looking for other things to find out this angle here. Okay. What I do have, if you look carefully, is that same bow tie shape that we've spoken about before. Let me just draw over it. So ABD, I'm looking for another angle on the circumference coming from those same 2 points, and that's this one over here. Okay, so that's telling me that these two angles are equal. So ABD is going to be 22 degrees. The next one asks us for ADC. So ADC is this angle here. It's important to notice that, well, you might be thinking we could use one angle down here, but we don't have these, so I have to use something that I've already got. It's important to notice we have a cyclic quadrilateral. Okay. All 4 points are on the circumference. So what I'm going to do first is I'm going to add up these two. That's 57. And in a cyclic quadrilateral, opposite angles add up to 180. So I'm going to do 180, take away 57, which gives me 123. Okay, so that one there is 123 degrees ADC. And then finally CAF. CAF is from here to here, so it's that angle there. And this is where our alternate segment theorem is going to come in. So here's our tangent. Here's the triangle that angle is kind of adjacent to there. And again, let's have a look at the kind of the Z shape, but not the alternate angles. Okay, so that's the angle I want. At the end of that Z is that there. That whole angle is 57 degrees in that triangle. So this one here is also 57 degrees using the alternate segment theorem. This question is asking us to find angle BCD. Let's just label that first. That's that angle there. I don't immediately see a way to find that. So I guess we're going to have a look at this angle here, A, and see if there's anything we can do with that. That angle A is subtended by D and C. And if you look here, this angle is also subtended by those same 2 points. We've got that kind of bow tie shape with all the points on the circumference. So that means that this one here at B is also equal to 32. So let's fill in that already. So this one is 32 degrees. The next thing I've spotted is that we have 2 equal lines here. So this is an isosceles triangle. So this one down here is also going to be 32 degrees. And then we've got a triangle here, and the angle we're trying to find is the remaining angle. So we'll do 32 out of 32, that's 64. And we're going to do 180 subtract 64, which is 116. So that means our remaining angle there is 116 degrees. Part B looks a little trickier. Here we've got a tangent, and although we do have a radius here, the angle is going not to the radius but to one of those other lines, so it might be an alternate segment theorem question. We're looking for angle AOC. Because they don't say, I presume they mean the acute, or I think it's an acute angle there rather than the reflex one. Because I've got this angle 42 degrees, I think that's the first one I'm going to start with and figure out what I can do with that. Let's draw over the tangent, and let's draw over the triangle which connects to that tangent there. And let's make that kind of that usual Z shape we use with the alternate segment theorem. So it's this one here. So already I can see that that one here is going to be equal to 42 degrees. So let's fill that in. And now for this one here, what we've got is we've got the angle at the centre, and we've got the angle coming from the same point but at the circumference. And the angle at the centre is twice the angle at the circumference, so this one here is going to be 2 times 42, 84 degrees. Here we've got quite a long question. It tells us we have a cyclic quadrilateral. What I can also spot here is that we've got a tangent, and we've got no radius or diameter, and we've got triangles connected to that tangent. So that's telling me that there's a good chance we're going to be using the alternate segment theorem at some point. First of all, we're asked to find CBD. So let's just draw over CBD. I'm looking if there's any other angles that are subtended by the same 2 points, and there's one down here, look. Okay, and they're both at the circumference. So we've got that kind of bow tie shape, so this angle and this angle are equal. So I know that CBD is going to be 42 degrees. So that's that first one done. And let's label it on the diagram too. The next one asks for ACB, so let's draw over that. ACB. So that's this angle up here. Now, although this angle is the same, we don't know what it is yet. That 85 doesn't seem that helpful yet. Let's see if it is the alternate segment theorem. I think it is. So here we've got our triangle, and here we've got our tangent. And again, we can make that kind of Z shape we've spoken about before. Except it's not alternate angles, it's the alternate segment theorem. So it's the angle at the end of that Z and this one here. So that means that this one here is going to be 55 degrees. ACB is 55 degrees. Let's add it to the diagram and put it on our answer line. Next, we're asked for angle ADC. Let's draw that in first. And we're wanting this angle here. Now, if I knew this angle here, then I could use the fact that it's a cyclic quadrilateral. And actually, I do have enough information to figure that out. Because this is a straight line, I can do 85, add 42, and subtract that from 180. So first of all, 85 add 42 is 127. Let's subtract that from 180. That is 53. And then for this cyclic quadrilateral to work, I need all of this angle here. So 42 add 53 is 95 degrees. I realise I could have figured that out a lot quicker by doing 180 take away 85. Never mind. And then these opposite angles in a cyclic quadrilateral add up to 180. So 180 take away 95 is 85 degrees. BCD is next. Let's just get rid of these lines. Okay, BC. BCD is this one here. To do that, again, it looks like it's part of that kind of quadrilateral, and the only thing that would be missing to be able to figure that out is this angle here. Can I work out this angle? Yes, I can, using this triangle here. Okay, angles in a triangle. So this angle here is 95, this one is 55. Let's add those up. That makes 150. And then subtract that from 180, angles in a triangle, and I get 30. So this little bit here is 30 degrees. Now I'm going to use my cyclic quadrilateral, which is here, and use the fact that the opposite angles add up to 180. So this whole thing here is equal to 72. The diagram's getting a bit messy. So 72 degrees here. So this whole one here is 180 take away 72, which is 108, and that's the angle that we were looking for, 108 degrees. The last angle that they want is angle PAD. Let's get rid of some of these lines again. So where is PAD? PAD. Now we could use alternate segment theorem, but actually if I look at this, I've already got all of these angles added up here. I could add them up and then I've got angles on a straight line. So because this is a straight line, I've got 55 here, I've got 72 here, and they must add up to 180. So 55 plus 72 is 127. And I'm going to do 180 take away that is 53. So PAD is 53 degrees. This question wants us to find angle ABC, but it wants us to give reasons as well. Okay, now we've got a tangent, we've got a triangle connected to that tangent, so it could be one where we're going to use the alternate segment theorem. Let's first of all just show where ABC is. We're trying to find that angle there. I don't immediately see an obvious way to find that. We do also have a cyclic quadrilateral, so if I know this angle here, then I can work out that one. Let's see, if this angle over here, let's connect up that triangle. Yeah, and it is the alternate segment theorem. Let's have a look at the kind of Z shape we've got. And because it's not alternate angles, it's not this one here, it's this one over here. So this one here is 64 degrees. Okay, it's at the end of that little Z there. So let's get rid of those lines and write that this one here is 64 degrees. And then using the fact that it's a cyclic quadrilateral, those two things add up to 180. So 180 subtract 64 is equal to 116. Right, let's fill in all of those reasons. So first of all, we worked out angle ADC is 64 degrees. The reason for that is angles in the alternate segment are equal. And then we use the fact that ABC equals 116. Because opposite angles in a cyclic quadrilateral add up to 180 degrees. So 1 to 180 degrees. This question here is an unusual one because we've also got parallel lines within our circle. Now if I just draw over this angle here, there's another angle which is subtended from these same 2 points, DA, and that's this one over here. So using our kind of angles in the same segment, a kind of bow tie shape, we already know that those two angles are going to be equal. So let's fill this one in here as being 32 degrees. But then the fact that they're parallel lines means we can also use alternate angles. So that one is also equal to that one there. So this one is also 32 degrees. And then we've got two of the three angles in a triangle. So let's do 32 add 32, which is 64. And then to find the missing angle, we're going to do 180 take away 64, which is 116 degrees. In this question, we once again have a tangent, and although we have the radius as well, we have an angle which is connected to a triangle. Okay, so probably we're going to be using alternate segment theorem at some point. I'm not sure. It's also important to notice that we have parallel lines, and we have the diameter of a circle. So let's see, first of all, we're asked for angle QSR. That's this one here, QSR. Now that I know that this one's equal to that one, but I don't know what that one's equal to. Let's maybe connect up that triangle there and draw in our tangent. Is it alternate segment theorem straight away? Yes, it is. I've got my kind of Z shape, but again, it's not alternate angle, so it's not that one. It's this one at the end here. And from the alternate segment theorem, QSR is equal to 42. So they're straight away starting you off with the alternate segment theorem for 1 mark there, which I think is kind of tricky. The next one we're asked for is PQS. PQS, so that's that angle there. Here it's important to realise the fact that we have those two parallel lines, which means that we can use alternate angles. PQS, look, we've got that Z shape there, and because they're parallel we can use that. So PQS is also equal to 42 degrees. which again is tricky. If you didn't get that first part using the alternate segment theorem, it would make that one difficult to do. Next is POS. POS. Now this is an angle which is at the centre. So we're going to look for an angle which is at the circumference, which comes from those two same points P and S. And it's either this one here or this one here. Okay? So PQS is subtended at the circumference, POS is at the centre, and the angles at the centre are twice the angles at the circumference. It makes that kind of arrowhead type shape. So this one is double 42, so 84 degrees. So POS is 84. Again, tangent and a triangle connected to that tangent, so probably something to do with alternate segment theorem. It wants us to find the value of x and the value of y. Probably in that order is the easiest way to do them. Let's draw over our tangent, and x is inside this triangle here. Okay, for alternate segment theorem, let's try and do some kind of Z shape, but again, it's not alternate angle, so it's not this one here that's the same, it's this one over here. So that one over here, using the alternate segment theorem, is equal to 38 degrees. So already we can figure out that x is 38. Let's label it on the diagram and fill it in on our answer line. Now for angle Y, it's important to spot that we've got two parallel lines there. So I suppose that would be important. Using that parallel line and this one here, I can make a Z shape, which is alternate angles, which means that this one over here is also going to be 38. So let's fill that in. And now the only one I would need is this one here, and then I'd be able to work out y. So the other thing that we need to notice is that this is a cyclic quadrilateral, this whole thing here. All points are on a circumference. And opposite angles in a cyclic quadrilateral add up to 180. So this one here is 120. And now I'm going to add these two together and subtract from 180. 120 add 38. Is 158, and angles in a triangle add up to 180, so subtract from 158 and we get 22 degrees. So angle Y is 22. This question immediately looks absolutely horrible. Thankfully they're only asking us to put a ring around the diameter of the circle. For this one, the circle theorem we need to remember is that the angle subtended by the diameter is 90 degrees. So for instance, if I have a diameter here, then this angle here, which comes from the two ends of the diameter, is equal to 90. Now I don't spot any 90 there, so I guess we're going to have to do a bit of calculation. It's clearly not going to be this tiny acute angle there. Those are both 85, so it's not that. This missing one here, let's work that one out. 94 add 6 is 100. Take that away from 180 using angles in a triangle. So this one here is 80 degrees. So there's nothing to do with that. Here, 8 add 82 is 90. Take that away from 180 and that makes this one here 90. So this one here is a right angle. And it is subtended by these 2 points, D and E. So that means that DE must be the diameter. That one's going through the centre. It does not look like it at all, okay? It really doesn't look like it's going through the middle, but it has to be DE. In this question here, things to spot is that we've got two tangents and we've got the radius coming from both of them. When we've got the tangent and the radius, the angle between the tangent and the radius is 90 degrees, so let's already fill that in. We're trying to find angle x over here. Now the circle theorem that I think we're going to have to use for this one is that kind of arrowhead one where I've got the angle at the centre and the angle at the circumference. And the angle at the circumference is half the angle at the centre. So we need to find this one here first. We're already almost there because we've got a quadrilateral. It's not a cyclic quadrilateral because the points aren't all on the circumference. But the angles still add up to 360 degrees. So we're going to do 90 plus 90 plus 44. And that adds up to 224 degrees. And then I'm going to subtract that from 360. Okay, that is 136 degrees if I'm not mistaken. So this one here is 136. And the angle at the centre is twice the angle at the circumference. So I'm now going to divide that by 2. Which is 68 degrees. So x is 68. Things to notice in this question is we have a tangent, we don't have a diameter, so alternate segment theorems in play here. And we've also got these two equal sides here, so we've got an isosceles triangle. I'm going to draw over the tangent, I'm going to draw over the circle connected to it, and I'm going to look for a kind of Z shape that includes that angle, but it's not this angle here, it's this one over here. So that one there already I know is 50 degrees. Now I can use the fact that these two lines are equal, so we've got an isosceles triangle. So this one is also 50 degrees. Then I'm looking for angle TPQ, which is this one here. So let's add them up. 50 add 50 is 100, and subtract that from 180. Using angles in a triangle, that one is equal to 80 degrees. Part B has a little bit of algebra here. First of all, let's find the value of W. I guess the only thing we're going to do first is maybe find this one here. We've got angles on a straight line, so we'll do 180, take away 68, which is 112. So this one here is going to be 112 degrees. For W, opposite angles in a cyclic quadrilateral add up to 180 degrees. So 180 take away 112 is going to be 68. So W is equal to 68 already. And again, we've got a cyclic quadrilateral, which we're going to use for 3x and 2x. Opposite angles add up to 180, so 3x plus 2x must be equal to 180. 3x add 2x is 5x. So then let's divide both sides by 5. So 180 divided by 5 is 36, is that right? Yeah, 36 degrees. Although question 10 looks horrible, it's actually not too bad. Let's start with x first, and to work out x you can pretty much ignore the top bit of the diagram. Let's draw over that angle x. And angle x is subtended by A and B. The only other angle that I can see subtended by A and B is this one here. Now watch out, it kind of looks like that bow tie shape, but this time this part is at the centre of the circle. It's not subtended at the circumference, so they're not equal, because this one's at the centre. This one here, which is at the circumference, is half of that. So angle x is 55 degrees, half of 110. Now for angle y, let's draw over y there. That's subtended by D and E. And this one over here is also subtended by D and E. And this time they are both at the circumference, okay? Both angles, the point of the angle is right on the edge of the circle. So angle y is equal to 24, they're equal. So y is 24. This question wants us to show that PQR is an isosceles triangle, so I guess that means showing that we have two equal angles, and it wants us to give a geometrical reason for each step in our working out. Okay, we've got x is an acute angle, we've got a tangent, we've got a triangle connected to the tangent. Because we've got that triangle connected to the tangent already, we need to be thinking about the alternate segment theorem. And let's draw that kind of Z shape there. And it's this one here which is equal to x. So we know that that angle there is equal to x because of the alternate segment theorem. Let's get rid of all of those lines. Let's write that down. So we could call that angle RPQ equals x because angles in the alternate segment are equal. Okay, what other information do we have that might help us here? QR bisects angle PQB. PQB, so that's that. Now, if we're told that QR bisects it, to bisect means splits it exactly in two. So that means that that is equal to that. Those two angles there are equal. Okay, so that means that this bit here is also equal to x, okay, because that line is bisecting that whole angle. So I've got that those two things are equal. So let's write down that. PQR equals x because of what they said there, because QR bisects PQB. Just to convince them I know what I'm talking about, maybe I'm going to write down 120 divided by 2 is equal to 60. Now there's one more thing that I think I'd like to just include here, because there's one other possibility, and that's the fact that all of these are equal, and it wouldn't be an isosceles triangle, it would be an equilateral triangle. However, it does say here that x is less than 60. Okay? So since x is less than 60, that means that PRQ can't be 60, okay? They're not all 60. Because in an equilateral triangle, they'd all have to be 60 degrees. PRQ is not equal to 60, and for that matter, nor are any of the others. So it's not equilateral. And then we know that RPQ equals PQR. Therefore, because we've got those two angles equal, we have an isosceles triangle. Another question that looks kind of horrible here. First we want to find angle ADC. Let's draw over it. ADC. Things to notice, we've got a tangent. I do have a triangle connected to that tangent. We've also got the radius. We've also got, really important to notice, is a quadrilateral with all 4 points on the circumference. There, and there. And we're trying to find ADC, that one there. And look, we've got the opposite angle in that quadrilateral, and because it's a cyclic quadrilateral, they must add up to 180. So I can do 180 take away 131, and that's going to tell me ADC. So that first one, not too tricky if you spot that. So 59 degrees for ADC. Let's fill it in on the diagram as well. I'm maybe going to fill it in just by writing that this one here is 39 degrees. And together they make 59. Angle AOC is next. AOC. So this is an angle at the centre. So the ones that are useful to know are the angle at the circumference subtended by the same 2 points. So let's see, is there an angle at the circumference that comes from A and C? Yes, there is, the one that we just found there. So it's like that bow tie shape, but careful, this time one of them is at the centre. This one here is 59, because this one is at the centre, it's double the one at the circumference. So we're going to do 2 times 59, so 108 degrees, that one at the centre there. Did I say 108? I meant 118. Next is angle BAT. BAT. Now the only way to find out something like that normally would be using something like the alternate segment theorem. So there's our tangent. Let's draw the triangle which includes that side BA. So there. And there's that triangle connected to it. Let's try and do that fake kind of Z shape. So Z involving that angle BAT. That's that one there. Okay, and it's at the end of that Z, it's that one there. So 20 degrees is going to be equal to BAT using the alternate segment theorem. So BAT using the alternate segment theorem is 20 degrees. Let's put it on the diagram as well. Finally, in this question, we're asked for angle OAB. So OAB is here. So it's this angle we're looking for. And here it's just important not to forget that actually this is the centre of the circle. And the angle between the tangent and the radius is 90 degrees, so if this one here is 20, that remaining part there is 70 degrees because they've got to add up to make 90. So that last one, easier than it looks at first. You're probably starting to notice how often alternate segment theorem comes up, and this is another one of those where we have the tangent, we've got a triangle connected to the tangent, and we're going to draw our kind of Z shape. Except, as always, it's not alternate angles because we don't have parallel lines, so it's this one and this one over here which are equal. So this one over here is going to be equal to 70 degrees, so let's get rid of all of those lines again and put this one here is 70. The actual angle we're trying to find out though is x. Now it's important to notice that we've got an isosceles triangle because these two sides are equal, which means that these two angles are equal. So we're going to do 180 take away 70, which is 110, and then we're going to divide that by 2. So both of those two angles at the bottom there are 55 degrees. So that means x is 55. Again, a tangent, triangles connected to it. The first one we're asked to find is angle DCB. Now actually we're not using the alternate segment theorem straight away. The thing that we're going to spot is that we've got 4 points all on the circumference, so we can use a cyclic quadrilateral. So this one here is plus that one here is equal to 180 degrees. So angle DCB is 180 take away 98, so 82 degrees, because opposite angles in a cyclic quadrilateral sum to 180 degrees. Is PBQ a tangent to the circle? Okay, so we're told that it might be or it might not be. So I guess if we know that this is 82 degrees, I guess we're going to try and use alternate segment theorem and see if it actually works. Okay, so PBQ. Now, if it is, when I draw my triangle here like that, and if I try and do my Z shape, and it's not this one here, but it's this one over here, so these two should be equal. But they're not. So that means that this can't be a tangent, because if it was a tangent, we'd be able to use alternate segment theorem. So I guess that means that PBQ is not a tangent. So no, because if it was a tangent, then according to alternate segment theorem, those two angles would be equal. So what are they? QBC would be equal to the one that's 57 degrees, BDC. We've got a tangent to the circle in this one, and we've got triangles connected to that tangent. We want to find RQT. RQT is over here. I think it's also important to notice that we've got a cyclic quadrilateral here. So to be able to find that, it would help to know this one over here. So if we can figure out this one here, then we know that those two add up to 180. So let's see if we can figure out this one over here. I'm going to connect up this triangle, and then we've got the tangent here. And then if I use the alternate segment theorem, there's my kind of Z, but it's this one over here that's equal to 70 degrees, not this one, but this one. Let's get rid of all of those lines. So that one there is equal to 70 degrees. And then, yeah, sure enough, using a cyclic quadrilateral, those two things have to add up to 180. So 180 take away 70 is 110 degrees. This question looks quite busy. We've got a cyclic quadrilateral, we've got a tangent, we've got triangles touching that tangent, so it could be alternate segment theorem. We want to work out x and y. Usually they put these in order, so probably x is the easiest one to figure out. Now, if it's a cyclic quadrilateral, and we're trying to work out this angle here, that means that if we work out the one over here opposite, then we know that one. And it's quite easy to work out that one there, because we can use angles on a straight line. So this one here, because we've got a straight line, this one here is 80 degrees. And then opposite angles in a cyclic quadrilateral add up to 180. So already we can quickly figure out that x is equal to 100 degrees. Let's also label that on the diagram. Next angle we want to find is angle y here. Now, to be able to work out angle y, because we've got this tangent, I think it's probably something to do with alternate segment theorem. Let's maybe draw the triangle and draw over the tangent, and then let's see if we can make our kind of Z shape, including that angle there. And because it's not alternate angles, it's not this one that's equal to that one, it's this one over here, which is that one. So yeah, that means that according to alternate segment theorem, y is going to be 55 degrees. Things to notice on this question are we've got a tangent, we've got triangles connected to the tangent, we've also got the radius there, we've also got an angle at the centre, So we could be using a lot of circle theorems in this one. We've also got a cyclic quadrilateral as well. The first thing we're asked to find is BCD. BCD is there. And to me, this first part looks like we're going to be using that cyclic quadrilateral. These are the 4 points on the circumference. Careful, the cyclic quadrilateral can't have one of the points at the centre, so it's definitely not with that. So these two angles must add up to 180 degrees. So I'm going to do 180 take away 51. And 180 take away 51, if I'm not mistaken, is 129 degrees. Okay. So using the cyclic quadrilateral. The next thing we're asked to find is ABD. ABD. It's not clear straight away. There's not another angle that's subtended by AD. Let's connect up that triangle then. And let's draw in the tangent and see if we can make a Z shape using the angle that we're given here, 64. It's not alternate angle, so it's not that one, it's this one here. And so that one is going to be equal to that one. So that one's 64 degrees using alternate segment theorem. So that's that one done. Next is obtuse angle BOD. BOD, so it's this angle here. Okay. For this one here, so it's subtended by D and B. There is another angle subtended by these, and that's this one over here on the circumference. And the angle at the centre is twice the angle at the circumference. Okay, and it comes from those same 2 points. So what I'm going to do is I'm going to times that 51 by 2. 51 times 2 is 102 degrees. So this one is 102. Oh, and that's it. Not too difficult in the end, that one. In this question, we've got a tangent again. We've got triangles connected to the tangent. So alternate segment theorem probably for at least some of these. Our angle BAD is what we're asked for first. Okay, let's connect up that triangle. Let's draw in the tangent as well. And let's see if we can make our kind of Z shape using that 55 degree angle there. Remember, it's not alternate angle, so it's not this one here, it's this one at the end. So that one's equal to 55 degrees and using the alternate segment theorem. Let's get rid of the lines and draw that one in then. So 55 degrees. BAD is equal to 55 degrees because angles in the alternate segment are equal. And what do they want us to do next? Angle BCD. Okay, BCD is this one here. And here, if you notice, we've got a cyclic quadrilateral, all four points are on the circumference. So I'm going to do 180 take away 55, which is 125. Okay, so angle BCD equals 125 because opposite angles in a cyclic quadrilateral sum to 180 degrees. Okay, again, a tangent and a triangle connected to the tangent. It's almost like the alternate segment theorem comes up so much that it gets a little bit repetitive. Okay, so we're trying to find the value of x, but I'm not sure if that's quite the correct one for alternate segment theorem just yet. That's the angle that we're using here is our kind of Z shape. It's not that one, it's this one here. So this one here is 40 degrees using the alternate segment theorem. So let's fill in that one, that's 40 degrees, alternate segment theorem. Now we're going to add those up and subtract from 180. 77 plus 40, 117. and then 180 take away 117 is 63 degrees. In this question, again, I see a tangent, I see triangles connected to that tangent. I can see we've got a cyclic quadrilateral, so lots of stuff we could be using. We're asked for angle CDB first, CDB. Are there any other angles subtended by the same 2 points, C and B? Yes, there are. This one over here. So we've got that bow tie shape with both angles on the circumference, so those two angles are equal, and that's why it's only one mark there. So this one over here is also going to be 25 degrees. Let's get rid of the line and put that in. That's using angles in the same segment. Next is ACB. ACB, like that. So that one would be the same as this one over here, but I don't know what that one is. So maybe this is the alternate segment theorem. Let's connect that up. Let's draw along the tangent, and let's see if we can make some kind of useful Z shape. That's that, including the 40-degree angle. So there, it's not that one that's equal to that one, it's this one here. So yeah, that one there is equal to 40 degrees using the alternate segment theorem. Okay, then DCE. DCE is that angle there. So we could also extend that. So is there another angle which is subtended by those same 2 points? Yes, there's this one here, which would be the same. But do we know what that one is? We don't yet, but we could work it out. Okay, so if we work out this one, then it's going to be the same as that one there. There might be a quick way to do this one, but I can't immediately spot it. So let's work out what this angle here is, and to do that I'm using this triangle here. All three of these angles have got to add up to 180. Okay, 40, add 25, add 55, and then we've got the missing bit of that angle there. So let's add those all up and subtract from 180. So 40 plus 55 plus 25. So that bit there is equal to 80, add that is 120. So 180 take away that is equal to 60. So that little bit there is equal to 60. And then here, these two are equal. So that one and that one, we've got that kind of bow tie shape, so they're both equal to 60 degrees. If there's a quicker way to do that that I've not spotted, then maybe you can let me know in the comments below. So DCE is equal to 60 degrees. Angle YAD is next. YAD. To be able to find an angle between the tangent and a line like this, often it's using the alternate segment theorem. So I'm just going to make that line a little bit longer. I'm going to draw in the triangle that connects to the tangent there. I'm trying to find this angle here, so let's draw a Z shape which kind of includes it. And it's not this one that's equal to this one, it's this one over here. So that means that YAD is equal to 60 degrees, the same as that one at the top up there. So that one is also 60. Things to notice in this question is we've got a tangent and we've got triangles connected to the tangent. We've also got a cyclic quadrilateral, and the first thing we're asked to find is ADC, which is over here. And for this one I think we're going to use the cyclic quadrilateral. These two angles have to add up to 180 degrees. Okay, so that one on the right there is 110 degrees, they've got to add up to 180, so that's going to make this one here 70 degrees straight off. Next one, ACP. ACP. To find an angle like that, usually it means we're going to have to use the alternate segment theorem. So let's draw the triangle which is connected. We're trying to find this angle here, ACP. Let's draw a Z shape which includes it. It's not alternate angle, so it's not this one here. It's this one over here. So ACP is the same as what we just found. It's also 70 degrees. Okay. Oops. 70 for both of them. Next, PCB. So that's that tiny little one there. Okay, so again, I think to find an angle like this, I think we're going to have to use alternate segment theorem. So maybe do it in red, so that's too thick. So there's the tangent. The angle we're trying to find is between there, so I'm drawing that line in, and now I'm going to draw the triangle that includes that line there. And let's see if we can draw a kind of Z shape which includes that angle PCB. So it's not this one and this one, it's this one and this one over here. So PCB is equal to 30 degrees, again using the alternate segment theorem. In this question, we've got a tangent, and this time we have got the radius and the tangent, so they're going to make an angle of 90 degrees. We've also got this kind of arrowhead shape with the angle at the circumference and maybe at the centre. Let's see, we're asked to find the value of x, and it's 3 marks, so I think this is one where we're just going to start to fill in whatever we can and see how far we can get. And the first thing I'm going to use is the tangent and the radius. I'm going to work out that missing bit there, because they have to make 90 degrees. That means that this bit here is going to have to be 37, okay? 53 out of 37 makes 90 degrees. Okay, the next thing I'm going to use, what other angles could we possibly find here? Let's work out this one here. Okay, and we can work out this one because this is a radius and so is this. So here we've got an isosceles triangle, in fact. So this one is also 37. And using those two, we can then work out this one. 37 add 37 makes 74 degrees. And then we're going to do 180 take away 74, which gives us 104. Okay, still no closer to finding that one, but if we find this one, then can we go back and find that one? I don't see any quicker way to do this. If you spot a quicker way, you can let me know. Because now I'm going to use the angle at the centre is twice the angle at the circumference. Okay, so what I mean by that is this one is subtended by C and B at the centre. We've got this arrowhead shape, so this one is subtended by the same 2 points at the circumference, so it's equal to half of that. So it means that this one up here is 52. Okay, and now I'm going to start using the angles in this arrowhead quadrilateral. So first I need this reflex angle here, so 360 take away 104, 256. And to find x, I'm going to do 360, subtract 256, subtract 52, subtract 20, and that'll give me what's left by doing the 4 angles in this quadrilateral. This is the quadrilateral I'm talking about, this arrowhead. Okay, maybe there's a quicker way that I haven't spotted. Like I say, if you spot it, let me know below. Quickly going to use my calculator just to speed it up a little bit. I got 32, seems like a reasonable answer. Here we've got a tangent, and again triangles connected to the tangent. The first angle we're asked to find is angle PRS. So from P to R, R to S. So it's this angle here we're looking for. I can't see another angle subtended by the same thing, so I think we're going to be using the alternate segment theorem. as always seems to be the case in these questions. And here's a kind of Z shape which is going to include that angle. So it's this one, 58 degrees, and this one up here. So PRS is going to be 58 degrees, same as that one down there. So let's get rid of those lines and write that in. 58 degrees. Next is PQR. P to Q to R. Now, this one here, it's important to realise that we've actually got a cyclic quadrilateral, and opposite angles in a cyclic quadrilateral add up to 180. So for this one we're going to do 180 take away 74. So what's that? 106 degrees for PQR. And then RPQ. RPQ, this one here. Don't think it's going to be through more circle theorems. I think this is one where we're going to find it using some of the missing angles. And here we've got two of the angles in a triangle. So let's add those up and subtract from 180. So add them up. What have we got? 70, add 50, 120, 132. Subtract that from 180 and we get 48. So this one here is 48 degrees. And RPQ is that angle there. So it's angles on a straight line. So now we're going to add up all of these things, and it's the little bit that we've got left. So 58 plus 48 plus 27, so what's that? 90, 106, 126, 133, I believe, and then 180, subtract that, is 47 degrees. So no tangents in this question. We're asked to find ACB. Okay, this is subtended at the circumference. There is an angle subtended at the centre by the same 2 points. So first we're going to need to find that angle, and then we'll use that to find the one at the circumference. So we want to find this one here. Well, the first thing to notice is we've got the radius both sides here. So this angle here is also 28 degrees. We've got an isosceles triangle. Then we're going to add those two things up. 28 add 28 is 56. And then to find this angle here, we're going to do 180 subtract 56, which is 124 degrees. And then, like I said, we've got 124 at the centre. From the same 2 points, we've got an angle subtended at the circumference. So that one is half of the one at the centre. So 124 divided by 2 is 62. So ACB, 62 degrees. Part B, all this could be is the alternate segment theorem. We've got tangent, we've got a triangle connected to the tangent, and we're trying to find angle RPQ, so this one down here. I think to find this one first we need to find the one that's up here on the top right, so we'll draw our kind of Z shape. This one here is equal to that one down here, so that one there is 47. Then we're going to use angles in a triangle. 52 add 47 is 99, and then 180 subtract 99 is 81 degrees. So RPQ is equal to 81 degrees. This question looks a little bit horrible. Things to notice is we do have like a few cyclic quadrilaterals in here which could be useful. So for instance, that there is a cyclic quadrilateral. We also have a few others, like this one here. This is also a cyclic quadrilateral as long as the points are on the circumference. And there's also one here. So there are possibilities to use the cyclic quadrilateral in this question in a few places. We're asked to find u, v, w and x. Usually makes sense to start with whichever one they said first, so u first. Is there another angle subtended by those same 2 points? Yes, there is. There's this one that we already know up here. We've got that bow tie shape, so that means that those two are equal. Okay, so u is equal to 20 degrees. Let's add that to the diagram and put it on our answer line. Next is v. Let's see if we can use a similar thing with v. So v is subtended by these 2 points. This angle down here is also subtended by these 2 points, so that means that these two are equal. We don't know what this is yet, but we can work it out pretty easily because we've got this angle here and this angle here, and they're a triangle. So let's do that. Let's add up 72 and 56. What's that, 128 degrees. And because those are angles in a triangle, 180 take away 128 is 52. So this one here is 52. And this one are angles in the same segment, so that one is also 52 degrees. W is next. And I think this is the one where I am going to use the cyclic quadrilateral. I'm going to use this cyclic quadrilateral here. Opposite angles in the cyclic quadrilateral add up to 180 degrees. So that one plus that one make 180 degrees. 180 take away 72 is 108. So 108 for W. And finally, angle X. Okay, for this one here, I could think of it as a triangle. Let's add up these 3 angles. This angle, add this angle, add this angle makes 180. So here we've got 72. 20 add 52 also makes 72. So let's add those 2 things up. 72 plus 72 is 144. And then we'll do 180, take away 144 for the remaining angle. So 36 degrees for X. In this question, it asks for a geometrical reason why this is a cyclic quadrilateral. Well, the thing that we know about cyclic quadrilaterals is that opposite angles add up to 180. Okay? So the geometrical reason is the opposite angles in a cyclic quadrilateral sum to if I really wanted to be thorough, I could then write, look, 101 add 79 equals 180, so it works for that pair, and 85 add 95 again makes 180, so it works for that pair as well. Job done. We've got a tangent, we've got a triangle, so it's yet another alternate segment theorem. Let's draw over the tangent and angle X, and we're trying to find angle X, so let's draw a kind of Z shape that includes it. And it's not alternate angles, so it's not this one, it's this one over here. So that means X is equal to 55 degrees. Because angles in the alternate segment are equal. Another tangent from the point S touches the circle at V. Give a geometrical reason why SV. Oh, okay, well let's try and so something like that. So here's our point V, and here's our triangle SVR. Give a geometrical reason why SVR is isosceles. Okay, so this is using one of the circle theorems that we've not used so far, and that is that tangents from the same point are equal. Okay. Tangents from the same point are equal in length. Okay, by which I mean this thing, this line here is equal to this one here. So we've got two equal sides. So we've got an isosceles triangle. First time we've had that one so far. Okay. Here we've got a cyclic quadrilateral. It asks us to find the value of y. I guess to find out y, we're going to need to know the value of x. So we're not going to start with this pair, we're going to start with this pair here. Okay, and those opposite angles must add up to 180. So 2x plus x plus 60 is 180. Let's collect like terms. 3x plus 60 is 180. Subtract 60 from both sides, so 3x equals 120. Then divide both sides by 3, we get x is equal to 40. Okay, so now we can find out this angle at the top here, 4x minus 87. So 4 times 40 minus 87. 4 times 40, 160. Subtract 87, and so 73. And then y, well, that and 73 add up to 180. So to find y, we're just going to do 180, subtract 73, and what's that? 107 degrees. In this question, we're asked to show that this is a cyclic quadrilateral. So to do that, we want to show that these two angles add up to 180, and these two angles add up to 180. To do that, we're going to start with one of the pairs, find out what x is using that pair, and then check that it works in the other pair of angles. I'm going to pick this pair randomly. Okay, you could pick the other pair, it would work just as well. Just as well. So let's do those two angles. X add, not 2x, x add 3x minus 40. Those two things have to add up to 180. Let's simplify the left-hand side, 4x. Then let's add 40 to both sides. So 4x equals 220. Then divide by 4. X equals 55. So here I've got 55. Here I've got 3 times 55, which is 165. Subtract 40, 125. So sure enough, those two add up to 180, but I definitely need to check that value in these two now. So let's substitute x equals 55 into here. 2 times 55, take away 5, equals 110, take away 5, so 105. That's angle P. Let's do R as well. X add 20 is 75 degrees. So now I just need to convince them that opposite angles add up to 180. So S plus Q equals 55 add 125, which is 180, and P plus R equals 105 plus 75 equals 180, and then convince them that I know what a cyclic quadrilateral actually is. This is 5 marks, so let's not give them an excuse to take a mark off us. So I'm now going to write opposite angles sum to 180, therefore it's a cyclic quadrilateral. In this question, I can see there's a cyclic quadrilateral, which may be helpful. I can also see we've got this kind of arrowhead, which involves the centre there, so that might be useful too. The question first of all asks us for C, B, D. And yeah, that's the one with the arrowhead. So if this one here is 124, the one subtended in the same segment at the circumference is half of that. So it's going to be half of 124, so 62. Let's write it in first. So CBD equals 62 because the angle subtended at the centre is twice the angle subtended at the circumference. I think that should be enough. I might just pop in, like at the end, I might just also write just in the same segment, just to be sure. Okay, work out angle BAD, giving a geometrical reason for each step of our working. Okay, this one's 4 marks, right. BAD. So I'm thinking that the way to figure this one out is to use the cyclic quadrilateral, so to work out this angle here, down here first, and then we can use the fact that they add up to 180. So let's make it our mission to work out this one down here. Okay, so here we've got a radius and another radius, so we have got an isosceles triangle. So let's use that first of all. Okay. I'm not worrying about writing that in yet. First I'm going to write because OCD is an isosceles triangle. Okay. I'm going to do my working out, so I'm going to do 180 take away 124. That's 56, and then divide that by 2. It's 28. So these two angles here, 28 degrees. Let's fill in our step working out. OCD is an isosceles triangle, so this angle here, angle OCD, equals 28 degrees. I've put my working out for it up there, otherwise I'd need to write it in somewhere here, I think. Then I'm going to do 28 add 35. Okay, so 63. So this whole thing here is 63 degrees. And then I'm going to do 180 take away 63. And that's equal to 117. So that's what angle BAD is. Oops. and that's because opposite angles in a cyclic quadrilateral sum to 180 degrees. That should be enough for the 4 marks.